Good morning, everyone, and welcome to my lecture. Today, I'm gonna talk about the compressibility of soil. Here we go. With superimposed loading, soil layers experience a certain amount of compression because of the several factors, which are the formation of soil particles, expulsion of water and/or air from void spaces, and relocation of soil particles. Generally, soil settlement resulted from loading may be divided into three main categories: immediate or elastic compression, primary consolidation, and the secondary compression. Immediate settlement, owing to the elastic deformation of dry, moist, and saturated soils without any change in their water content. Immediate settlement calculations are usually based on equations derived from the theory of elasticity. Immediate settlement under an area bearing a uniform pressure on the ground surface can be obtained by this equation given here, where SI is the immediate settlement, Q is the uniform pressure acting on the ground surface, B is the width of the foundation or the diameter of circular foundation, E is the modulus of elasticity of soil, nu is the Poisson ratio, and IS is the influence factor depending on the shape of loaded area. To use the equation, the modulus of elasticity and the Poisson ratio must be worked out. For foundations resting on saturated clay soils, immediate settlement occurs under undrained conditions. The suitable value of Poisson ratio is then 0.5. For other types of soils, typical values of Poisson ratio are presented in the table here. If you notice, it ranges from 0.2 to 0.5. On the other hand, modulus of elasticity under undrained condition for fine-grained soils may be determined from undrained triaxial tests or from in situ tests such as cone penetration test or pressure meter test. For coarse-grained soils, empirical methods are usually utilized based on either standard penetration test or cone penetration test data. Typical values of the modulus of elasticity for different types of soil are given in the table here. It ranges from 18 megapascal to 70 megapascal. For most soils, the modulus of elasticity increases with depth. So use of a constant value of modulus of elasticity results in a conservative value. Settlement estimations under the center and a corner of flexible and a rigid loaded areas, and also for average settlement under the area as a whole, are given in the table here. For most cases in practice, simple settlement calculations are adequate on the condition that reliable values of soil parameters for the in situ soil have been obtained. It should be appreciated that the precision of settlement predictions is much more affected by inaccuracies in the values of soil parameters than by shortcomings in the methods of analysis. Here it is, a practical example to illustrate how to calculate the immediate settlement, in other words, elastic settlement of foundation. A building foundation of 4 times 2 meter carrying a load of 1.2 meganewton is located at a depth of 3 meter in soil over a layer of clay 4 meter thick, for which the value of modulus of elasticity under undrained condition is 50 megapascal. This layer is underlain by a second clay layer of 8 meter thick, for which the value of modulus of elasticity is 80 megapascal. The second layer is underlain by a rock layer. You are asked to determine the average immediate settlement under the foundation. Compute the immediate settlement. The equivalent modulus of elasticity of 2 clay layers is required. We can obtain the equivalent modulus of elasticity based on harmonic mean, which is the thickness of first layer times its modulus of elasticity plus the thickness of second layer times its modulus of elasticity divided by the total thickness of first and second clay layers, which is 70 megapascal. Pressure at the base of footing is the ratio between the load and the area of foundation, which is 150 kilonewton per square meter. Since the clay soil layers are fully saturated, Poisson ratios for them can be taken as 0.5 as stressed earlier. To calculate the average immediate settlement, we need another parameter called influence factor, I sub S, as shown here. This can be obtained from the related table shown earlier based on the ratio between the length and the width of foundation, which is 2. Now, putting all these related data in the equation as shown here, we can figure out immediate settlement, which is about 4.2 millimeter. Now, before learning how to calculate consolidation settlement, let us first understand the process of consolidation. Since soil is a heterogeneous system, it may be expected that a load applied to soil mass would be carried in part by soil skeleton and in part by pore water. This sharing of the load can be typified by means of a simple analogy. As shown in the figure, the spring in the cylinder represents the compressibility of soil skeleton, and the bore diameter shown here of the valve represents the permeability of soil. The cylinder itself simulates the condition of no lateral strain in the soil mass. Now, suppose that a load is applied to the piston with the valve closed as shown in figure A. In this case, piston will not move as long as the valve is closed, and no load can be transmitted to the spring, as illustrated In figure, the whole load will be carried by water in cylinder and none by the spring because there is no drainage. This condition in the field is referred to as undrained condition. If the valve is opened, as shown in figure B, water in this case will be forced through the valve at a rate controlled by the bore diameter, and this will allow the piston to move downward and the spring to be compressed as the load is progressively transferred to the piston as shown in figure D. Since drainage starts, the load applied to the piston will be carried in part by water and in part by the spring. Finally, as shown in figure C and D, the whole load will be carried by the spring and none by water. The piston will come to rest. This condition in field is referred to as drained condition. Similarly, when saturated clay soil in the field is loaded, all of the applied load will be transmitted to the water in soil mass, generating excess pore water pressure as illustrated in the standpipe here. The excess pore pressure is above the groundwater table. Since clay has very low permeability and water is incompressible, theoretically at time t0, the entire stress increase will be carried by water and none by soil skeleton as shown in the figure. Here you see the total stress increase variation with the thickness of clay layer and the excess pore pressure variation with that within clay layer resulted from the surface loading and the effective stress. Immediately after loading, there will be no drainage and no dissipation of excess pore water pressure, and therefore there will be no transference of stress to the soil skeleton. Thus, the effective stress will be zero immediately after loading. With the lapse of time, which may take days, months, or even years, the excess pore water pressure will progressively reduce as the pressurized pore water flows out. While this happens, delta sigma will be gradually passed on to the soil particles, and this means that the effective stress increases as shown in the figure here. Nevertheless, the magnitudes of effective stress increase and the excess pore water pressure at different levels will be different depending on the distance of the drainage path. In our case, there is only one-way drainage, which is at the top of the clay layer. And there is no drainage at the bottom because it is underlain by rock mass, which is impervious. Now, the excess pore pressures at upper levels of clay layer are higher than those in the middle and at the bottom. Correspondingly, the effective stresses are higher at the upper levels but lower in the middle as well as at the bottom. This means that some of the stresses are passed on to the soil skeleton. Meanwhile, drainage continues and the settlement of clay layer takes place slowly. Theoretically, at infinite time, when the excess pore water pressure is completely dissipated, in other words, when the pressurized pore water has entirely drained, the effective stress will increase by delta sigma as illustrated in the figure. This means that the stress acting on the ground surface is totally carried by soil skeleton. This progressive process of drainage under surface load application and the related transmission of excess pore water pressure to the effective stress as the cause of time-dependent consolidation settlement in soil layers. To estimate the settlement of clay layers in the field, a series of consolidation tests are performed in the laboratory through audiometer shown in the figure here. I will give you a brief information about these tests. The details can be found in related textbooks or in the laboratory manuals. A soil sample, usually 75 millimeter in diameter and 20 millimeter in height, is placed inside a metal ring as shown in the figure here, with a porous stone at the top of the sample and another one at the bottom. During this test, soil sample is loaded using prescribed stress increments. For each stress increment, changes in the sample height are monitored through a micrometer dial gauge mounted on the loading plate, as shown here, and recorded within at least 24 hours. It is important to note that at the end of the test, for each increment loading, the stress on the specimen is the effective stress. The question is, how reliable are the results of laboratory tests regarding that only a small soil sample is tested? Will it correctly represent the field conditions? Well, there is always apprehension about applying results from the laboratory tests to solve large-scale field problems. Engineering practice shows that the results obtained from the laboratory tests may be very different from the field data. The problem results from the size of soil samples tested. That is to say, small laboratory samples do not generally represent the presence of larger voids or inclusions of other materials, which are prevalent in the field. Let's get back to the subject. In consolidation test, the void ratio at the end of each increment period can be computed from the displacement readings and either the water content or the dry weight of the sample at the end of the test. According to the phase diagram given here, the water content approach of calculation can be carried out as follows. In the figure, H sub 0 is the thickness of specimen at the beginning of testing. Delta H is the change in thickness during testing, which can be obtained from the difference between the initial and final readings of dial gauge. A sub 0 is the initial void ratio just at the beginning of testing, which is equal to A sub 1 plus delta E. A sub 1 is the void ratio at the end of test. Remember that at the end of test, the soil sample is still fully saturated. So the degree of saturation in this case is equal to unity. E sub 1 then can easily be obtained by W sub 1 times GS. W sub 1 is the water content measured at the end of test. G sub S is the specific gravity of soil solids, as you know. Delta E is the change in void ratio. Delta E can easily be obtained from the figure, which is equal to delta E over 1 plus E sub 0, which is equal to delta H over H sub 0. What is that? This is the definition for the vertical strain of soil sample. The definition on the left side is in terms of void ratio, and the other one on the right-hand side is the definition in terms of thickness of soil sample. In a similar manner, delta E can be calculated up to the end of any increment period, and the related void ratio for each stage of loading can easily be computed. Obtained test results are plotted and analyzed to obtain the compression index and the coefficient of volume of compressibility needed for the calculation of consolidation settlement. The laboratory data from odometer tests are plotted as the effective stress versus void ratio using a logarithmic scale as shown in the figure. If you notice, the curve consists of three parts: the recompression part, linear part, and the unloaded, reloaded part. The recompression part accounts for the soil disturbance. When the soil is removed from a certain depth in the field, there will be stress relief. Now, the compression index is obtained from the linear and steep part, which is also called virgin compression line of the experimental curve. Let us consider 2 points, namely A and B, on the linear part of the curve. The compression index is then defined as the ratio between delta E, which is the difference between void ratios corresponding to A and B, and log delta sigma prime, which is the difference between effective stresses corresponding to A and B points. If a soil is overconsolidated, it will be represented by a point on the unloaded, reloaded part of the E log sigma prime plot. By the way, what is meant by overconsolidated soil? If the present effective stress is the maximum to which the soil has ever been subjected, the clay is said to be normally consolidated. On the other hand, if the effective stress at some time in the past has been greater than the present one, the soil is said to be overconsolidated. The maximum value of effective stress in the past divided by the present value is defined as the overconsolidation ratio. A normally consolidated soil has an overconsolidation ratio of unity. Overconsolidated soil has an overconsolidation ratio greater than unity. The overconsolidation ratio can never be less than 1. Overconsolidation is generally the result of geological factors, for example, the erosion of overburden due to glacier motion, wind, wave, or ocean currents, the melting of ice sheets and therefore reduction in stress after the glaciation or permanent rise of the water table. Overconsolidation may also take place due to man-made activities. For instance, pulling down an old heavy structure and building a lighter one instead. Now, considering a point at a depth H as shown in the figures, there is no change in the vertical effective stress due to self-weight of soil, but there is a change in the stress increase due to surface law. The stress increase delta sigma 1 due to heavy structure is greater than the stress increase delta sigma 2 due to lighter structure. In this case, the soil layer is said to be overconsolidated. How can the maximum effective vertical stress that has existed on the soil in the past be known and/or found out? The maximum past effective overburden pressure is also named as the pre-consolidation pressure. There is a simple graphic construction suggested to determine the pre-consolidation pressure from the laboratory E log sigma prime plot. The procedure is thus: initially we need to draw E log sigma prime plot as shown in the figure based on the laboratory test results. The first step is by visual observation determine the point A of maximum curvature on AB part of the E log sigma prime curve. Second step, draw a horizontal line through point A. The third step, draw the tangent to the curve at point A. And the fourth one, bisect the angle between the tangent and the horizontal through point A. The fifth step, produce back the straight line part BC of the curve to intersect the bisector. And finally, draw the vertical through the point of intersection of the bisector to obtain the value of sigma C prime. That's it. Whenever possible, the pre-consolidation pressure for an overconsolidated clay should not be exceeded in construction. If it is exceeded, then the compression will be large. Contrary to compression index, the coefficient of volume of compressibility is defined for a much narrower range of stresses using an arithmetic scale for the applied stress shown in the figure. This makes coefficient of volume of compressibility rather sensitive to changes in stresses. and its value can significantly vary depending on the stress change. Now, considering 2 points A and B on the curve as shown in the figure, the coefficient of volume of compressibility can then be defined as delta V over delta sigma prime. Now the question is, what is the engineering approach to deal with consolidation in practice? There are two main important questions which engineers are needed to find solution for. The first one is, what will be the maximum settlement? And the second one, how long will it take? The following sections, therefore, will discuss how to calculate soil settlements and time of consolidation. In order to estimate one-dimensional consolidation settlement, the value of either the coefficient of compression index or the volume of compressibility is required. Let us consider a site comprising a normally consolidated soil, on which we wish to construct a structure and assume that the increase in vertical stress due to structure in the middle of soil layer is delta sigma. In this case, the final vertical stress will be sigma 0 prime plus delta sigma. Sigma 0 prime is the effective vertical stress due to self-weight of soil in the middle of soil layer. The increase in vertical stress will then lead to the soil settlement following the virgin compression line as shown in the figure. The primary consolidation is then obtained by the equation given here, where delta E is equal to log sigma sub 1 prime over sigma sub 0 prime. If, on the other hand, soil is overconsolidated, we have to consider two cases based on the magnitude of delta sigma. Case 1, if sigma sub 1 is less than pre-consolidation pressure, as shown in the figure here, then consolidation occurs along the recompression part, and the primary consolidation in this case is obtained by the equation given here. Case 2, if sigma sub 1 is greater than pre-consolidation pressure, as you see in the figure here, we have to consider two components of settlement. One along the recompression part and the other is along the virgin compression part. In this case, the primary consolidation is obtained by the equation given here, where delta E is equal to delta E sub 1 plus delta E sub 2. H sub 0 is the initial thickness of the soil layer subjected to consolidation. Sigma sub 0 prime is the initial effective stress in the middle of the soil layer before structural load. Delta sigma is the stress increase in the middle of the soil layer due to structural load, and sigma sub 1 prime is the final effective vertical stress in the middle of soil layer after structural load. Delta E is the difference between the initial and final void ratios before and after structural loading. In the calculation of primary consolidation settlement, you may need to follow a procedure outlined here. The first step is to calculate the current vertical effective stress and the current void ratio at the center of soil layer for which settlement is needed. And the second step is to compute the applied vertical stress increase due to surface load at the center of the soil layer using the suitable method. And the third step is to calculate the final vertical effective stress, which is equal to present vertical effective stress plus the stress increase due to surface load. And the fourth step is to compute the primary consolidation settlement. Now, if the soil is normally consolidated, which means if the present effective vertical stress is equal to pre-consolidation pressure, then the primary consolidation settlement can be calculated using this equation given here. If the soil is, on the other hand, over-consolidated, in this case, the primary consolidation settlement can be computed using the equation given here. Notice that instead of Cc, we use Cr, which is the slope of the recompression part of E log sigma prime plot, because the pre-consolidation pressure in this case is greater than the present vertical effective stress. If the soil is overconsolidated and the present effective vertical stress is greater than the pre-consolidation pressure, the primary consolidation settlement can be calculated using the equation given here. In this equation, we have two parts, namely the recompression part and the virgin compression part of the E log sigma prime plot. It is also possible to calculate the primary consolidation settlement by using the coefficient of volume change. In this equation, H sub 0 is the initial thickness of the clay layer, and delta sigma as the change in vertical stress that brings about consolidation. Although compression index is constant, the coefficient of volume change varies with stress level. To take into account the variation of coefficient of volume change and or delta sigma with that, the graphical procedure can be adopted to calculate the primary consolidation settlement. In the figure here, you see the variations of initial effective stress increment, the coefficient of volume change, and the dimensionless product of m sub v times delta sigma prime with that. In an alternative way, the layer can be divided into sub-layers, and the product m sub v times delta sigma prime can be determined at the center of each sublayer. Each product is then multiplied by the suitable sublayer thicknesses to obtain the sublayer settlements. The settlement of the whole layer is then equal to the summation of the sublayer settlements. This technique may also be used to analyze the layered soil profiles where the soil layers have different compressional properties. The advantage of using this method is that the coefficient of volume change is readily determined from the displacement data in consolidation tests. So you don't need to calculate void ratio changes from the test data as needed in the determination of compression index. Secondary compression settlement is the change in the volume of soil resulted from the readjustment of the soil structure after the primary consolidation has ended. Based on the consolidation test data, a plot of void ratio versus the logarithm of time can be made as illustrated in the figure. Now, the primary consolidation is assumed to end at the intersection of the projection of the two straight parts of the curve as you see in the figure. Now then, the secondary compression index is defined as the slope of the secondary compression part between selected time intervals. Thus, the secondary compression settlement can be computed by means of the equation given here, where E sub P is the void ratio at the end of primary consolidation. E sub T is the void ratio at time T on the secondary compression part. H is the thickness of clay layer at the beginning of secondary consolidation. And T is the time at which secondary compression is needed. The total settlement of a foundation can then be given as the summation of elastic settlement, primary consolidation settlement, and the secondary compression settlement. Now we have a practical example for the calculation of consolidation as well as secondary compression settlements. A hospital building with its total load of 270 meganewton is planned to be constructed on a site composed of a 2-meter thick sand layer underlain by 5-meter thick, normally consolidated clay layer, beneath which impermeable rock layer lies, as you see in the figure, and the groundwater table is 1 meter below the ground surface. The building's raft foundation is rectangular one with a width of 30 meter and length of 60 meter. The laboratory tests conducted on soil samples collected from the middle of soil layers at site through boring reveals the following data. The unit weights of sand above and below the groundwater level is 16 kilonewton per cubic meter and 18 kilonewton per cubic meter respectively. The saturated unit weight of the alluvial clay is 17 kilonewton per cubic meter. Table 2 shows data from consolidation test run on the soft alluvial clay. The initial water content of clay layer is 68%, the specific gravity is 2.6, and the secondary compression index is 0.02. Question 1. What would be the primary consolidation settlement in the clay layer caused by the construction of hospital building? And the second one, what would be the total settlement of the clay layer 10 years after the completion of primary consolidation settlement? Note that time for completion of primary consolidation settlement is 2 years. The first step is to plot the effective stress versus void ratio depending on the consolidation test results, and then determine the compression index. This is already done for you. From the linear part of the curve, the compression index can be obtained as the ratio between two selected void ratios on the linear part and the corresponding effective stresses, which is about 0.70. The second step is to calculate the stresses acting in the middle of clay layer before the application of building load. So the total vertical stress in the middle of clay layer is equal to thicknesses of soil layers times their unit weight. The total stress in this case is obtained as 76.5 kilonewton per square meter. Pore water pressure is an easy one, which is calculated as 34.3 kilonewton per square meter. The vertical effective stress in the middle of clay layer is equal to total stress minus pore water pressure, which is about 42.2 kilonewton per square meter. The third step is to figure out the initial void ratio, which is equal to water content of soil times its specific gravity times the degree of saturation. Since the clay soil is fully saturated, the degree of saturation is equal to unity. In this case, initial void ratio can be calculated as 1.77. The fourth step is to compute the vertical stress increase in the middle of clay layer under rectangular raft foundation. For these, you can use Boussinesq approach, but for the simplicity, let us use the approximate method, which is 2-1 method. With this approach, the stress increase due to hospital building in the middle of clay layer can be obtained as 121 kilonewton per square meter. The final step is to calculate the consolidation settlement of clay layer. Since alluvial clay is normally consolidated, the equation given here will be used. Remember that the primary consolidation settlement for the normally consolidated soil is obtained using this equation. Putting all the relevant values in their places, we can calculate the primary consolidation settlement as 0.74 meter. In the calculation of secondary compression settlement, the first step is to determine the value of E sub P. E sub P is the void ratio at the end of primary consolidation, which is equal to initial void ratio minus the change in the void ratio during primary consolidation. Now remember that the primary consolidation settlement is equal to this equation given here. Now from here, we can define delta E as illustrated, and putting the values in their places, we can figure out delta E primary, which is the change in the void ratio after the completion of primary consolidation or at the end of primary consolidation. Now, the difference between initial void ratio and the change in void ratio during primary consolidation is equal to 1.36. In the second step, the thickness of clay layer after the primary consolidation is determined, which is the difference between the initial thickness of clay layer and the primary consolidation settlement, which is about 4.26 meter. In the third step, the secondary compression settlement is computed based on the equation given here. Now, the secondary compression period for the settlement calculation is 10 years, and the completion of primary consolidation settlement is 2 years. Other values are already given and calculated, so based on these, the secondary compression can be calculated as 0.03 meter. Finally, the total settlement can be obtained by the summation of primary consolidation settlement and the secondary compression settlement, which is about 0.77 meter. Notice that the secondary compression settlement is very low compared to the consolidation settlement. So is the elastic settlement. So these two are generally ignored in practice. So the main concern is primary consolidation settlement. Another practical example is a detached house experienced a differential settlement of 21 millimeter 2 years after its construction. The walls of the house, as you see in the figure, began to crack. A few of its doors and windows have jammed. The owner wonders if the differential settlement would continue. If so, what would be the expected total differential settlement? He therefore asked for the help of geotechnical engineer. In the solution of this problem, the first step is to go through the related foundation project, soil investigation report, if any, and the bearing capacity and settlement calculations. After careful examination, it was decided that the available data was not enough and a detailed soil investigation was needed. The soil investigation revealed that the thickness of clay layer was variable as shown in the figure. And it was assumed in the design of the foundations that the clay layer had a uniform thickness of 1 meter. In the second step, the vertical stress increases in the middle of the clay layer under each foundation are computed. For these, let us use the approximate method illustrated before. Now, based on this approach, the stress increase beneath foundation A and foundation B are 37 kilonewton per square meter and 83 kilonewton per square meter respectively. In the third step, the primary consolidation settlements under each foundation are calculated based on the given value of the coefficient of volume compressibility. Based on this approach, the settlements beneath foundation A and B are 0.023 meter and 0.105 meter respectively. In the final step, the expected total differential settlement is expected as the difference between the settlements of foundation A and foundation B, which is about 82 millimeter. That's it. Well, let me quiz you on the main points of today's lecture. The first question: consolidation is a phenomenon that usually occurs in which one? Fine-grained soils. Very good. Very good. So the answer is A. The second question: which of the following is the compression index? This is easy one. Yes, the answer is C sub C. Very good. The third question: a vertical stress of 100 kilonewton per square meter is applied to the saturated clay. When time approaches infinity, the excess pore water pressure will be which one? No, you are joking. Who said that? Yes. It should be 0 because at the end of consolidation, the excess pore pressure will have been completely dissipated. So the answer is A. Question 4. Which of the following statements is incorrect? Which one? B. Yes, you are right. Consolidation occurs due to expulsion of water. This is a wrong statement. Very good. And the question 5. The decrease in initial excess pore water pressure causes an equivalent increase in vertical effective stress and settlement decreases. True or false? But be careful. Read the sentence carefully. No, it is not. No, no. Yes, the answer is B. Now, the decrease in initial excess pore water pressure causes an equivalent increase in vertical effective stress. It's true up to here. But then the settlement decreases. This is not true. Settlement will increase. Question 6. The current vertical effective stress acting on soil is 100 kilonewton per square meter. The past maximum vertical effective stress was 200 kilonewton per square meter. So the overconsolidation ratio is, this is easy for you. Yes, the answer is C. Very good. Question 7. How is consolidation different from soil compaction? In the end, each process will densify the soil, causing a higher strength anyway. Any comment? If you remember, compaction is the process of removing air from soil because we add water and then apply compaction. In this way, we replace air with water. On the other hand, consolidation, as you have learned, is the process of expulsion of water from soils and mostly from clay soils. Question 8. What statement is not correct if the drainage of pore water is permitted. Waiting for your reply. Which one? B. Jolly good. Settlement decreases with time is wrong. Settlement increases with time is the correct statement. And the final question. An overconsolidated soil has experienced vertical effective stresses greater than its current vertical effective stress. True or false? Well then, the answer is A. It is a false statement. That completes my lecture. Thank you for listening. Hope to see you soon. All the best.